Welcome, everyone. My name is Shtub. I'm head of training at ScyllaDB. The topic of today's talk is database latency and caching. That's a big topic. My focus will be on NoSQL, and specifically, I'll be using ScyllaDB as an example to demonstrate the topics that I'm talking about. Like I said, I'm head of training. My background is as a software engineer. I am based in Israel, and I've been with ScyllaDB for about 7 years, so for quite a while. The agenda for today is I will give an overview of ScyllaDB and where it fits in the NoSQL world. Then I will talk about design and architecture. I'll talk about why latency matters in general and why we should care about it. Then I'll talk about common ways in which latency problems are solved using caching, including different caching strategies that are popular. I'll talk about problems and pros and cons in some of those caching strategies. And then I will look at the option of using ScyllaDB as a cache replacement. And if we have time, I might also talk about some use cases and how some users are solving their caching issues. Before I get started, I will say that, this talk is live. It's not pre-recorded. I'm using 2 screens, so I'm also looking at the chat window as I'm talking. If there's some technical issue, you cannot hear me, or the wrong slide is displaying, let me know. Also, if you have questions, ask. I'll try to make it as interactive as possible. Tell me if I'm going too fast or too slow, and I'll try to adapt according to what's interesting for you. 2 useful resources before I get started: ScyllaDB University, our online learning training resource center. You can see the website. It's university.scylladb.com, and it has a whole bunch of training material around NoSQL and around ScyllaDB. The material is completely free, and to get started, all you have to do is create an account, and then you can just take lessons. The lessons are in form of videos, hands-on labs, there are quizzes, and so on. So I recommend you check that out. And we have a documentation website that's more in-depth regarding specific procedures and such. Okay. So let me start by giving a high-level overview of NoSQL and ScyllaDB. Maybe before I do that, let me get a better feel for what is your experience, the people that are listening right now. I cannot really see you, but what's your experience with NoSQL? Are you new to NoSQL? Did you already use it? Are you currently using it? Did you use ScyllaDB before, or Cassandra or DynamoDB for that matter, which are similar databases? So if you could just quickly answer in the chat window, what's your experience with ScyllaDB, with NoSQL, with other databases? I know how much in depth I should go in the overview part. So let's take another few seconds so people have a chance to answer in the chat window. Again, my question is, what's your experience with NoSQL, and are you familiar with ScyllaDB or DynamoDB or Cassandra? Okay, so I see not too many people answered, but from those that did answer, some are new and some are experienced, familiar with different databases. Okay, so I will go into the introduction, just so you understand where we fit in the NoSQL world. I'll try to go over it quickly. So this is the CAP theorem, which states that in distributed systems, and specifically distributed databases, we try to strive for 3 different attributes: availability, consistency, and partition tolerance. Availability meaning that the system is able to serve requests at all times. Consistency means that Well, one way to define it is that for every read, we will get the latest write. And partition tolerance talks about what happens when there is a network failure. The CAP theorem states that we have to give a preference to 2 out of the 3 attributes. And on this slide, you can see different databases. Of course, it's by no means an extensive, wait, let me maximize it. It's in no way including all the databases out there. There are like, I don't know, 100 popular databases, but a selected few. And we can see here that ScyllaDB, together with Apache Cassandra and Amazon DynamoDB, give a preference to high availability over consistency, whereas other databases such as MySQL give a preference to consistency over availability. Okay. There is another more granular model which talks about the trade-off between latency and consistency, but let's skip that part. Okay, so let's look at different databases according to the data model, and specifically NoSQL databases. Again, there are many different types. This doesn't cover all of them, but it's a pretty good selection. So one data type or data model is document store databases. An example is MongoDB. And there we simply store the data as predefined documents. Think about XML or JSON. So they're pre-formatted, and that's easy to use. An even more simple data model is the key value database, okay? And there, just like it sounds, we have a key and a value. Say the key is user1 and the value is Mike. An example from these type of databases is Redis. That's a popular one. And like everything, it has its pros and cons. The main advantage is that it's very simple to use, right? It's just a key value. A more advanced data model would be wide column databases, also called sometimes key value stores. And there we can think about our data as tables that have rows and columns. Okay, so we have the concept of tables. It's more advanced. And this will be the focus of the talk today. Examples from this type of data model are Apache Cassandra, that's a common one, Amazon DynamoDB, and ScyllaDB. Another one is graph stores, graph databases, like Neo4j, like Janus Graph, and others. And their data is modeled according to edges and vertices and the relationship between them. Okay, so that brings me to ScyllaDB. ScyllaDB is a NoSQL distributed database that's built to provide predictable performance at scale. Here we have, quite a random list of some of our users, some names that you're probably familiar with. They're from different industries, and we have use cases from many different industries. Maybe the most common ones I would say are ad tech, video streaming and gaming, but also financials and many others. I won't go into it, but if you're interested in a specific industry or use case, you could find on our website different user stories, and they share how they're using ScyllaDB for their use case. So some of the attributes of ScyllaDB, and let me say that in general, many of the concepts that I will talk about today, specifically when I talk about the architecture of the database, are relevant for ScyllaDB, which would be the focus, but they're also relevant for other databases like Apache Cassandra and Amazon DynamoDB. Okay, so the attributes are, oh, the slide is stuck. Thank you for that. I see that now it moved. I'll keep an eye on it. Sorry about that. Okay, so some of the attributes of ScyllaDB, like I said, performance. And when I talk about performance, actually that will be a focus of the talk today because we're talking about latency. So when I talk about performance, I mostly mean two things. I mean throughput. And when I talk about throughput with ScyllaDB, we're talking about millions and even billions of queries per second. So that's a very high throughput. And we're talking about latency, which is mostly the focus of this talk today. So when we're talking about latency, we're talking about typically sub-millisecond queries with a P99 latency of single-digit milliseconds. And I'll explain what that means in just a bit. Global scale, so like I said, it's a distributed database. We have multiple nodes that work together to serve requests. These nodes can be anywhere in different data centers, and it's easy to scale out the cluster by adding more nodes and scaling down the cluster if that's needed. Ease of use, so it's easy to maintain, and yeah, if you have questions about that, let me know, but that's not the focus today. Okay, so ScyllaDB comes in two different flavors. One is ScyllaDB Cloud, which is a database as a service offering. And there, just like it sounds, we take care of managing the database for you, and you can just use it as a service. And we also have Scylla Enterprise, which if you choose that option, you manage the database yourself. And with both options, you can use different cloud providers. So you're not locked into AWS or GCP or any other provider. You can choose where you want to run it. Okay, I mentioned that ScyllaDB focuses on high availability. And one of the ways to do that is by using multiple data centers and multiple availability zones within a data center, and that ensures high availability. In ScyllaDB, as well as Apache Cassandra, by the way, there is no single point of failure, okay? And that means that even if one node becomes unavailable, then the system can still continue to serve requests, or even if there's a network partition, the system continues to be up and running. It has a lot of built-in redundancy. Like I said, there's no single point of failure. We don't have the concept of leader nodes and follower nodes or master-slave nodes or any other name you want to call it. Each node can serve requests. Each node holds a part of the data, and data is replicated to multiple nodes in the cluster, okay? And again, that means that even if some nodes become unavailable, or even if an entire data center becomes unavailable, the data would still be available and the users would not experience any downtime. There are different reasons that we might want to use, or why we might want to use multiple data centers. And this is for a single cluster. For a single application, we're using multiple data centers. Does anyone have any idea why we would want to use multiple data centers? So the question is...
Disaster recovery?
Disaster recovery.
Sorry for interrupting.
Yeah, yeah, that's fine. You can also answer in the chat window. So one reason, disaster recovery. Does anyone have any other ideas? The question is, why would we want to use multiple data centers for the same application? Why would we want to run our database on multiple data centers? Any other ideas besides disaster recovery? Let's give people a few more seconds.
Improve the speed.
Performance, speed, okay. Proximity to user. Okay, so everything you said is correct. More efficient, load balancing. Okay, so let me sort of like summarize it. So what you said is correct. One reason, disaster recovery, I can also look at it as high availability. Even if, say, an availability zone within a data center becomes unavailable, or an entire data center goes down, very unlikely, but can happen, then the other data centers would still be able to serve requests. ScyllaDB is topology aware, and it knows where each node is and on which data center. And it has built-in redundancy, so data is replicated between data centers. Okay, so that's one reason, availability and disaster recovery. The second, like some of you said, is for speed and performance. So getting data across from, say, the US to China takes time because they're far away. So that's just the physics of it. And it would make more sense to serve users from a more proximate data center to where they are, just for performance reasons. A third reason would be, I didn't see anyone say this, would be for governance or regulation reasons. So in some jurisdictions, there's a requirement to store the data of the users from that area in a specific data center. So maybe, for example, in our application, we have to keep all the data of EU users in the EU data center. Okay, so by using multiple data centers, we can configure it that way as well. And by the way, I won't get into it, but it's possible to configure the database so that data is replicated asynchronously between the data centers. So a user would read or write to a data center. He wouldn't have to wait until the data is replicated to the other data centers, which takes more time. So I mentioned high availability and disaster recovery. This photo is from a fire that took place, I don't remember, but like 3 or 4 years ago, I think, in one of the cloud providers. They had an entire data center go down because of a fire. This was, I believe, in France, somewhere in Europe, and millions of websites became unavailable. But one of our users was using that data center, and their experience was better. They had no downtime at all with their application because they were using multiple data centers, and the other data centers were able to cover for the data center that had the fire. Okay, maybe a quick poll question. So how much, if you're currently using NoSQL, how much data do you have under management in the projects that you're working on in your database? So how many terabytes of data, or is it less than a terabyte? And between 1 and 10, between 10 and 50, 50 to 100, or 100 and more. If you can quickly answer this poll question in the chat window. The question again is, how much data do you have under management in the projects you're working on? Again, just to see that you're with me and that I'm not talking to myself, and maybe get an idea. Okay, let's wait for a few more seconds so more people can answer. Okay. Thanks for the answers. Okay, let me continue. Okay, so here we have a hands-on demo that you can run on your own. I'm not going to run it right now, but I did put a link to the GitHub code for it. By the way, I didn't mention it, but you don't have to worry about copying links or slides or whatever. I will share the slides with you by email after this call, probably tomorrow. So yeah, you'll get all the links that you see here and the slides as well. So this demo shows how you can, with just a few clicks, run 1 million requests per second on 3 I4I 8x large machines on AWS. And what you're seeing here in this screen on the slide is our monitoring stack, which shows us what's happening with our cluster. And you can see that there are 3 nodes, and we're getting P99 latencies of less than 1 millisecond. So both for reads and for writes. For writes, they're a bit faster. For writes, for reads, there's no data. And this is at 1.1 million operations per second, so it's quite a lot. And don't take my word for it, you can play around with it yourself. Here, I put a link to another lab that you can run on your own. Again, I'm not going to run it right now just because there's quite a lot of material I want to cover. But this link, maybe let me just open it so you can see how it looks like. So yeah, what you're seeing here is ScyllaDB University. And this is the Quick Wins Lab. It's very easy to start it. It actually opens within the browser. So what you're seeing here is actually a window within the browser. And if I launch it, yeah, it's classical. It's not working right now. Let's wait a second. Okay, if I launch the demo, then what this is going to do is it's going to actually start a virtual machine with a terminal. Let me maximize this. All right, so you can see the terminal, and we have instructions on the right-hand side. And in this very simple lab, let me increase the font size. What you can do is you can run a cluster. This cluster has just one node, just for the demo. You start it with Docker. You see, so I just clicked on the command and it copied it into the terminal. It starts a single node cluster. And what you can do with this lab is play around with the database, read data, write data, yeah, create a table, see how it works. But I'm going to leave that to you. That's an example of a lab that you can run. And again, there are many more labs and material on ScyllaDB University. All right, back to the slides. So that was the Quick Wins Lab. Let's talk briefly about ScyllaDB design and how the database works under the hood. Yeah, I didn't really mention it, but ScyllaDB is compatible with Apache Cassandra and with DynamoDB, two very popular databases. And we see quite a few users that are migrating from Cassandra or DynamoDB to ScyllaDB, just because they can keep their application as it is and just replace the underlying database. We also see migrations from other databases, but I would say those are the two popular ones. And again, I'm not going to go into details here. It's a bit out of scope, but one example of a user that replaced 40 Apache Cassandra nodes, they migrated their data to 4 Scylla nodes, so they significantly reduced the number of nodes, and the solution was 2.5 times cheaper. Of course, they had less machines. And not only that, they had 11 times better latency, which is the focus of the talk today. How exactly we achieve that, maybe I'll touch on that a bit. It has a lot to do with how the software is written and how close to the hardware it is. If we compare it to Cassandra, so ScyllaDB is written in C++, as opposed to Cassandra, which is written with Java. And there are other architecture decisions that I will talk about in just a bit. Yeah, you can see, again, you don't have to take my word for it. You can see the complete benchmarks and examples on our website, different users that migrated from different databases. And also, if you have a use case and you're thinking about using ScyllaDB, my recommendation is just reach out and get in touch with us, and we can help you determine if it's a good use case, if it makes sense. We can help you run a POC. We have a lot of experience in the field with different use cases. Okay, so I kept saying a node and I kept saying a cluster, and I never really explained what that meant. So let's go back for a second. What we see here is a 5-node cluster. A node is simply the ScyllaDB software running on a machine, on a server. Nodes work together to form a cluster, and the cluster works to serve requests, okay? We think about conceptually the cluster as a node ring, but all nodes interact or communicate with one another in a node-to-node fashion. So again, there's no single point of failure. And in a typical cluster in production, our recommendation is to use at least 3 nodes. Okay, so data is replicated between the nodes. Remember, high availability. And the number of nodes really depends on your application. Yeah, we have users running clusters with hundreds of nodes. Okay, so many machines. And today's modern machines can serve quite a lot of requests and have a lot of data. So that's very big data sets running billions of queries per second. Data replication. So again, high availability. I mentioned data is replicated across the cluster. Each piece of data that we write to the database is automatically replicated and copied to different nodes. And the number of replicas that the database holds is determined by the replication factor. The replication factor, also called RF, is something that is determined by the user depending on your needs. So when you create a key space, you define the replication factor. A key space is basically a container for tables. So all the tables within the key space will inherit the replication factor value from that key space. Okay, this is done automatically. So how does it look like? If we have a 5-node cluster, just like I showed you before, and we have a replication factor of 3, and imagine this cube is a piece of data. So when we write it to a node, say node 1, it's automatically replicated to other nodes, 2 other nodes as well. So at each time, we have 3 different copies of our data, and you can imagine that even if one node, say node 1, has a hardware failure or for whatever reason becomes unavailable, we would still be able to serve requests because we have 2 other copies of our data. Okay, this is a bit more, again, maybe going into data modeling, so I won't spend a lot of time on it, but it is important to understand. How does the database know where to store the data? So here we have an example table with 3 columns, pet ship ID, time, and heart rate, and a few rows. And if we were to write, say, the first row to our database, then the database would run something called a partitioner, which is a consistent hash function that it runs on a special column called the partition key. And according to the given hash function, it knows which nodes are responsible for that piece of data. Okay, so this is something that happens very quickly, and it goes together with the fast performance. The database knows very quickly where the data should go to and which nodes are responsible for it. So I talked about availability. Let's talk about consistency. In some NoSQL databases, again, like Cassandra, like DynamoDB, like ScyllaDB, we have something that's called eventual consistency. There are different types or levels of consistency. And the consistency can be defined by the user according to your application needs. You can set the consistency to be very high, but again, there's a trade-off that might be speed, and it also might require more hardware. And of course, also a trade-off with availability. Okay, so the consistency level is defined as the number of nodes that must acknowledge a read or a write request. There is a question if the recording will be provided after the meeting. I think it will. The slides will definitely be provided, but I think also the recording will be. So the consistency level is the number of nodes that must acknowledge a read or a write request. Some examples are 1, quorum, all, and there are other possible values. For example, if we set a consistency level of 1, it means that at least one of the replica nodes has to acknowledge the request. So if we have replication factor of 3 copies of the data, at least one of the nodes of those replica nodes has to acknowledge the request for that request to be successful. Okay, another option would be all, and that means that all 3 replica nodes must acknowledge the request. It's easy to understand that if we set the consistency level to all, we're going to have better consistency. But even if one node is down, then the request or the query is going to fail, right? So it's going to lower the availability. And there is a lab, the high availability lab, that you can play around with these values and see what would happen in a case where some nodes become unavailable with different consistency levels. The consistency level is set per query, so you might have a query that requires higher consistency levels and some queries that require lower consistency levels. Think of an example that, say, your application is writing data. It's an IoT application. You're measuring the temperature of the room, and every second you're writing that to the database, okay? So maybe the consistency level there can be a bit lower, because even if you miss 1 second, it's not a big deal. But maybe if once a day you're doing some analytical work, say processing the data for the entire day, then you probably want to have that query have a higher consistency level because you want your data to be more accurate, okay? Let's skip this one and go over to latency. Maybe let's see if there are any questions so far before I move forward. Yeah, if there are, just feel free to ask in the chat window. Next, I'll talk about latency and caching. Yeah, if somebody comes up with a question, just write in the chat window. So there is a question about vulnerability. I'm not sure. I don't know what that is. Okay, so I'm keeping an eye on the chat window. If you have more questions, let me know. By the way, also, if we don't have time for answering all the questions, or if you come up with a question after this talk, you could just shoot me an email or ask on the community forum, where you could just ask your questions and learn from other people. Our experts and engineers also hang out there. I also moderate that forum, so you can ask there. Let me write the link in the chat window. SQL inject or XSS. So I'm not sure. I don't know about that, but you can ask in more detail in the community forum. I'm sure one of our engineers will know. It's NoSQL, so I'm not sure how relevant that is, but again, I don't know much about it. Okay, so let's talk about latency. I mentioned that ScyllaDB is highly performant, and when I talk about performance, I typically mean throughput and latency. Throughput is how many queries per second we're performing, and with ScyllaDB, we're talking about up to millions and even billions of queries per second. But the second thing we talk about is latency, and latency is how fast do we get a response. Now, I'm a bit generalizing here, but I think it holds true in most cases. Whereas if users face issues with throughput, and that is they need to run more queries per second, they can typically throw more metal at it. That is, throw more money and just increase the number of servers. So instead of using, I don't know, 3 servers, they can use 6 servers or 6 nodes, and then they will be able to serve more requests. In many cases, that is something that scales and that's easy to do. However, with latency, that's not so easy to do. And even if we add more servers or more hardware, sometimes it doesn't decrease the latency and it even increases it. So why should we care about latency? There are different examples and different research that shows that users of applications, of websites, are very sensitive to latency. So imagine that you're, say, on an e-commerce website and the site hangs for 1 second. That's annoying. And some people would just drop and leave the website. And that translates to decreased revenue for that application. So there are different measurements for the number of bounced sessions and research that shows that the higher the latency is, more people drop, more sessions bounce. Yeah, and you can see the numbers here. I won't read it, but basically, just for example, if we jump from page load times that go from 1 second to 5 seconds, 5 seconds, the probability of bounce increases by 90%. So that's quite a lot. And later on, you can look at the resources here. So latency matters because we want to have faster response times that leads to happier users and to higher revenues, which is what almost all companies want. So an example from Walmart, they found that for every second improvement in page load times, conversion increased by 2%, and that translates to money. And more examples from other websites, including Grab, which is also e-commerce, they're a food delivery application in Asia. Okay, so I talked before, I don't know if you remember, about the P99 latency. So latency is typically calculated in the 15th, 90th, 95th, and 99th percentiles. And what does that mean? So while we might care about the average latency, what the user usually experiences is the worst case scenario, okay? So because we're a typical application, or even when we load a page, this requires many queries, say 100 queries. So even if the average is very fast, but there is one query that's taking longer, if loading the page is something that's done sequentially, then the entire operation would wait for that one query that's taking longer. And that's why it's common in real-time databases to look at the 99th percentiles, or the worst case 1%, also called the P99 latency. And that's a commonly used reference or measurement for database performance. By the way, there's a conference called the P99 conference, which happens once a year. It's virtual and it's free. And if high performance applications and databases is something of interest to you, I recommend you check that out. It's happening in October, I believe, this year. Okay, so I mentioned that the slowest 1% of the queries dominates the latency. That's what determines the user experience. And even if the average latency is okay-ish, if the P99 latency is not great, then the user will have a bad experience. What do many companies do? They use caching, okay, which brings me to the next part of our discussion. How do typically applications use caching together with a database? So let's look at different strategies. One strategy is to have a cache that's working together with the application, either in the application or on the server, on the same server as the application. This has pros and cons. The pros might be that it would be a bit more simple. The cons might be that there is tight coupling between the cache and the application. Imagine what happens if the application goes down. Then the cache becomes cold and we have to restart it and repopulate it. Or even the simple example of different applications that access the same database, that doesn't work if the cache is sitting together with the application. Another example is a write-through cache. Think about a common one is DynamoDB with the DAX, and there the user or the application is interacting directly with the cache. and the cache is interacting with the database. This is not very commonly used. It introduces another layer of complexity and another point of failure. So I'm not going to focus on that too much. But the next one that we see in this example using Redis is a more popular one. So what happens in this case is that the user or the application writes or reads from the database and from the cache. Now, the idea here is that Redis or the cache layer works in memory. It's smaller than the database. But this raises different questions, okay? So for example, what happens if we try to read data from the cache, the data is not there, we go and read it from the database, then do we update the cache afterwards? Do we not update the cache? So there are different considerations here, and it's quite complex, a complex thing to manage. Think, for example, of what happens when we delete data. Also, in terms of performance, if we have to query the cache, then the database, then the cache again, it creates extra hops, and this translates to increased latency. So sometimes the idea of the cache, well, not sometimes, the idea of the cache is typically to reduce latency, but sometimes it can result in the opposite, which is increasing the latency. And the other solution is to have the database in the cache. To have the cache in the database. And this is what we do with ScyllaDB. Some users choose to use ScyllaDB for caching separately, and they have another database. But many users choose to use ScyllaDB instead of their cache. So the cache is managed within the database, and there are many advantages of doing that. So let's talk about some of the problems that I already touched on. One would be increased latency, which is a bit of a paradox because the entire goal of the process of introducing a cache was to decrease the latency, but sometimes it increases it. Elevated costs. So we have another system. We have to maintain multiple systems. It adds additional complexity, right? Because we have multiple components. Think about availability. So what happens if the cache becomes unavailable or the database becomes unavailable? What do we do with the consistency, right? Because say the cache becomes unavailable and then we use the database and then the cache is back up and running. Do we populate data back from the database to the cache? There are different complex design decisions that we have to make if we choose this option. And this is important. It ruins the database caching, okay? Because a typical database has its own caching, but if we use an external cache, then the database cache is not used and it becomes cold or it doesn't provide any value to the user. Reduce security and additional admin complexity. Let's go into more detail about some of these. So increased latency, you can see an example here. Say we're having a cache like Redis and the database is Apache Cassandra. It takes 5 milliseconds to query Cassandra and another millisecond to query the cache. But sometimes we have to query both or even 3 hops. Say we go to the cache, the data is not there. We go to the database, we get the data, and then we have to update the cache. So that's 3 hops. Whereas in ScyllaDB, like I said before, we have less than 1 millisecond latencies without the cache or with using ScyllaDB's internal cache. Then what happens when we add multiple components, right? We want to have high availability, so we don't want a single point of failure. We have a few nodes of Cassandra and a few nodes of Redis. And that adds additional complexity and also costs more money. Okay. Whereas with ScyllaDB, you can have multiple nodes and the database would take care of the availability and the replication for you. Decreased availability. So yeah, again, this is complex. In ScyllaDB, we have something called hit-weighted load balancing. And that means that if a node goes down in ScyllaDB, and then after a while it goes back up, then the other two nodes in this example would continue to serve requests. And when that third node goes back up, its cache is going to be cold. Okay, so hit-weighted load balancing knows that after the node goes back up, its cache is cold, and it should route queries to the two nodes that have a warm cache. And slowly the cache of the node that was down would go back up, would become warm, and more queries would be routed to that node. Okay, so the database knows that, it does that for you. I don't think that's really possible to do if we're using an external cache. The database cache, in that case, Cassandra, in the previous example, would be called anyway. And then if a node goes up and down, or the cache or nodes in the cache go up and down, that would be something that would also ruin the cache and increase the latency, but can also harm the availability. So complexity. There's this quote that says, there are two hard things in computer science: cache invalidation and naming things. Yeah, so there are so many different cases we can look at, but let's look at one example. Say that I, first of all, go to get the data from the cache. If the data is not there, I get it from the database. But then should I update the cache afterwards, yes or no? And if I update it, do I do it synchronously or asynchronously? How do I handle data consistency? And what is the overall consistency of the system? So hard questions, and this is something that the user would have to manage at the application level, right? So it's hard to test, believe me, and there are many different things that can go wrong in such a system. So again, it's not easy to understand how consistent the system would be. Another important point is that we ignore the database knowledge. This is really important. Let me emphasize this again. Databases have a lot of context about the data. So think about the example that I just showed you before. We were having a Cassandra database, which is a key value wide column store. Think about data that's stored as rows and columns. And the cache is a key value store, like Redis. Okay, so what happens if we delete a table in our database? How do you handle that with a cache? Say you deleted an entire table. You would probably have to go to your cache, which has a different data model, it's key value, and you would have to find all these rows and columns and delete them one by one. Other structured data like user-defined types pose different challenges. Another example is time to live. So time to live in different databases, basically means that data in the database automatically becomes obsolete and is deleted after a predefined time period, say after, I don't know, 24 hours. So the database automatically deletes data after 24 hours. What do we do with the cache? Like the database, say Apache Cassandra, knew to delete the data, but then how do we delete it in Redis, which is our cache? We wouldn't even know that it was deleted, or I don't see any easy solution to this. It's complicated. And then think about more advanced things like indexes and materialized views, which are things that the database maintains for you, and you would have to manually do with your cache. Another thing is security. So in many databases like ScyllaDB, we have role-based access control, which is managed within the database. So we have different roles for different users that can do different things on different tables. How do we manage that on our cache? Do we duplicate the security system? What happens when we update the rules for who can access what? That introduces a whole new layer of security concerns. Another one is things that we do, queries in the database that we might do that would, in effect, harm the cache. So think about the full table scan that we do once a day. If we do a full table scan, it doesn't make sense to cache that data because an entire table going over all of our data is not going to fit in the cache. So it's just going to slow down the process, right? We're going to be adding information to the cache and evicting it because it's already full. So it would make more sense to not cache specific operations. Okay. Yeah, maybe one more thing that I didn't mention is that if we look at, say, this example, so the cache typically sits in memory. It's much smaller because, of course, memory, you can spend more money and maybe have a terabyte of RAM, but not a petabyte of RAM. That's too expensive. So obviously, the database has more storage than the cache, and it's way cheaper. So using that extra hardware for the cache also costs money. And if it doesn't actually decrease the latency, then it brings me back to the first slide where I presented latency. Even if we throw more money at it, we're not always going to get better results. It's a hard problem. So that brings me to ScyllaDB as a cache replacement. Another slide about the architecture. So I mentioned ScyllaDB is built very close to the hardware. It's built in C++. Everything happens asynchronously. It uses a shard per core architecture with specialized caching. We're almost out of time, but let me talk a bit more about the architecture. So other databases like Apache Cassandra use threading. So with threading, we have different threads competing for the same resources. And that's kind of what happens here with these different puppies. They're all competing for the same resource, this bowl of food. And that creates a mess. Some puppies are unhappy. With ScyllaDB and the shard per core architecture, each shard basically gets its own resources, and we don't have any context switching or competition for resources. So each shard gets its own networking, CPU, IO, RAM, and so on. And then we get something more like in the right-hand side here, where all the puppies have their own bowl of food. There's less of a mess, and puppies are happier. And this translates to lower latencies and higher throughput with databases. So there's a question about caching in ScyllaDB, how it's different from in-memory databases. Yeah, that would be very specific to the database that we're comparing to. But I have a slide on that. I don't know if that's exactly going to answer your question. But ScyllaDB implements its own cache, so it doesn't rely on the Linux page cache. The Linux page cache is basically something that's shared by all the applications running on the operating system. ScyllaDB works very, very close to the hardware, and it uses its own cache that's built from scratch to utilize all the resources of the hardware. So there is a question, let me read it. So what happens to data? Does it get stored in central place or just in each shard and data gets distributed? And what happens in the retrieval process? Okay, so we have nodes. Each node is composed of many shards according to the number of cores on that machine. And each core or shard is responsible for a piece of the data. Data is distributed ScyllaDB has its own cache, okay? That's using RAM, so it sits in memory, but it also uses, of course, NVMEs, so the hard drive, and there you can have a lot more storage. It's way cheaper than RAM, and ScyllaDB manages the cache for the database on its own. And by doing that, it avoids many of the problems that I previously showed you. So things like TTL, if the database erases data, it can automatically do that and erase the data from the cache. Many of the other things that I already showed you as problems, because the database has the information, it can take care of that on its own. We're almost out of time, just 2 minutes, so let me run through it. We also implement our own IO scheduler. We optimize for the newest instances, so now it's i7i, and we run tests with different instances. And even if you run ScyllaDB on your own machine, part of the setup process of the system is that it runs different like benchmarking scripts that test different options for the specific hard drive that you're using. And it uses optimized settings for that specific hard drive to achieve the best possible results with that hard drive. Okay, workload prioritization, I'll skip that. What you're seeing in this very loaded slide is our monitoring stack. And yeah, don't try to see the specifics, it's too small, but the point here is that with the monitoring stack, you can see exactly what's happening in the cache of ScyllaDB for a given replica, what's the hit-miss ratio, how hot or cold is the cache, and that gives you a pretty good idea of what's happening and allows you to optimize performance. We're almost out of time, but I'll say that you can enable or disable caching for each table. So maybe there are tables where it doesn't make sense to cache, and then you can simply disable that. And you can bypass the cache for a given query. So if you remember before, I said that if you do an entire table scan, you might want to not use the cache. So with ScyllaDB, you can simply bypass the cache for given queries. Customer use cases, Disney, Grab, and others. I don't have time to go over it. Available on our website. So to summarize, there are different options for using cache. It's quite complex. We have many examples of users that switched from external caching to using ScyllaDB, ScyllaDB's internal caching. They got lower costs and better performance. I highly recommend you check that out. If it's relevant for you, get in touch with us and we can help you understand if your use case is relevant. We have a training event happening on July 30th called ScyllaDB University Live. It's instructor-led. It's completely free. It's virtual. It's online. And you can register with this link. Like I said, I will send you the slides by email with the links to the labs. And that's it. I hope you learned something. Thanks for attending today. If you have any questions, get in touch with me. My email is guy@scyllaDB.com. Let me write it here. You can just shoot me an email. Also, I'm hanging around the forum and we're hiring. So if you're looking for a job, look at our jobs. You can also write me an email about that. And yeah, thanks for joining, everyone.